So next I'm going to do just a really simple problem. This one is not midterm caliber, I would say. It's just a simple problem to run through the equations to get you used to them. And then we'll do it in the next video. We'll do a more complex example. So here what we're considering is a reservoir of water that's 3.8 meters deep. And we're trying to calculate the force on this gate AB, which is 2 meters in height. And it tells you in the problem that this gate goes into the page 3 meters here, right? So it goes back into the page 3 meters. And so the question asks, A, sketch the hydrostatic pressure distribution on the gate, just on AB. That's a good idea. It's always a good idea to do that, get a physical sense of the problem. Then calculate the total force on gate AB, and then locate the line of action of that force relative to this upper hinge here at A. And just for a change of pace, I'm going to do this as a live problem on my laptop. Okay, I thought I'd solve this problem on the tablet just for a change of pace. So this is just a very simple problem just to demonstrate using the equations, and you can try some of the more complicated ones in the problem set. Okay, so part A asks for you to sketch the hydrostatic pressure distribution on the gate. So let me just re-sketch this here just quickly. We know from the previous presentations that the hydrostatic force increases linearly with depth. So it would be 0 at the free surface and increase as we go downwards. And I'm going to draw arrows here to show the distribution on the gate. So that's the pressure distribution on gate AB. So pretty straightforward. Let me just put some more dimensions on here. So this is going to be 1.8 meters. Okay, the next part of the question asks to find the hydrostatic force on AB. And the hydrostatic force on AB equals the gamma of water times the height of the centroid, the center of area of gate AB, times the area of surface AB. And we should keep in mind that this gate, in the problem statement, we're told that this gate goes back into the page 3 meters. So the gamma of water equals rho of water times G, which at 20 degrees C, the rho of water, you can look it up, it's 998 kilograms per cubic meter times 9.81 meter per second squared. That equals 9790 newtons per cubic meter. That's the specific weight of water at 20 degrees C. You'll be using that a lot. The area of the gate is simple. It's 2 meters high and it's 3 meters into the page. So it's 6.0 meters squared. Now, we need to get the height of the centroid. The centroid of this gate is going to be dead center in the middle. Draw it over here, the centroid. And so that distance there is going to be 1 meter. So the depth of the centroid, HCG, is going to be that 1 meter plus 1.8 meters. So 1.8 meters plus 1.0 meters, 2.8 meters. That's the depth of the centroid of the gate. Of course, the centroid of the gate is actually over here. The centroid of the gate from the free surface. So FAB, making the substitutions, is going to be 9790 newtons per cubic meter, 2.8 meters times 6.0 meters squared. You can see we have newtons per meter cubed, and we have meters cubed on the top, so that's going to give the force 164,500 newtons. So 164,500 newtons, 164.5 kilonewtons. So that's the answer to part A, and of course it acts to the right. We can see that from the pressure distribution. Make sure when you're drawing these, if you're drawing them on a midterm, that you show that the pressure vectors are perpendicular to the surface. So the next part of the problem is to find the center of pressure, or the line of action. It always acts below the center of area. We need to find out what that distance is. Let me go to the next page. Okay, and I'm just going to take a second to draw this gate in 3D. Okay, so what we're after is the location of the line of action relative to the centroid. And we showed in the previous derivations that the YCP, the Y location of the center of pressure relative to the centroid, is minus IXX sine theta H of the center of gravity times the area of the gate. And remember, this negative sign is telling you that the location of the center of pressure here, the force is going to act below the center of gravity, which is the center of area. So to calculate YCP, we need to calculate the second moment of area. So we need to calculate the second moment of area about a horizontal axis, this axis here, XX, which passes through the center of gravity. And you should recall that IXX is the width of the surface for a rectangle times the length cubed divided by 12. And so we have a gate that's 3 meters into the page, 2 meters high. So that's 3 meters times 2 meters cubed divided by 12. And that works out to 2.0 meters to the fourth. So now we can calculate YCP. It's minus 2.0 meters to the fourth. That's IXX. Now we next have sine theta. Now sine theta is the angle. If you project the gate up to the free surface here, it's the angle that the gate makes with the free surface. And in this case, it's a vertical gate, so theta equals 90 degrees. And the sine of 90 degrees is going to be 1. I'll just write it in there just to let you know. And we previously showed that HCG was the depth of the centroid from the free surface was 1.8 meters, and the area of the gate is 6.0 square meters. You can see we have meters to the fourth on the top and meters cubed on the bottom, so that's going to give you minus 0.1190 meters. So we're 0.1190 meters below the centroid. So just to be clear, let me go to the next page and just make a little drawing. So I'm going to draw the gate again here because the question asks to locate that force. So here's the hinge. So the force AB acts at 1.119 meters from hinge A. And that answers part C. And that completes this demonstration.